we could start. And our first speaker this morning from the other Cambridge, Jason Miller.
So thank you. So it's a great pleasure to give a talk here this morning. So what I'm going to be talking about is based on a joint work with Bertrand Duplantier and Scott Sheffield. And yeah, so my talk is going to have three parts to it. In the first part, I'm going to describe a construction that you can build by gluing together a pair of Aldous' continuum random trees. And then in the second part, I'm going to describe how this construction is related to understanding scaling limit problems for random planar maps, and in particular how they're related to Liouville quantum gravity. And then at the end, I'm going to describe some of the results that we've established in this direction. Okay, so what I want you to imagine on this slide is that you have two processes. So you have x and y are independent Brownian excursions on the interval from 0 to 1. And then what I've done here is I've picked a very large constant c. This is a random constant, and it's sufficiently large that if I draw the graph of x down here, my first Brownian excursion, then it's going to be disjoint from what I get if I draw the graph of c minus y, like that. And then what I'm going to do is I'm going to draw some green lines which lie under the graph of x, and I'm going to glue this picture together by identifying points if they can be connected by one of these horizontal green lines. And I'm sure, as everybody knows here, this construction yields one of Aldous' CRTs. Okay, so you get something that looks like this. And then I'm going to do exactly the same thing for the top graph, and this also yields another independent continuum random tree. Okay, so now we have these two continuum random trees, and what you can do is you can take them and you can glue them together, and the way that you do that is that in this picture on the left-hand side, you draw a bunch of vertical lines. So you have one vertical line for each x coordinate, and you declare points on this graph and this graph to be equivalent if they can be connected by a vertical line, so if they have the same x coordinate. And this induces an identification or a gluing of your two continuum random trees. And yeah, and so what we want to do right now is understand what type of structure you get when you perform this type of gluing operation. And it turns out that this is going to give you a pair which consists of a sphere together with a space-filling path. And this object, or this type of object, we've started referring to as a pianosphere, and this is actually based on a conversation with Rick Kenyon this past summer. So this is the pianosphere construction. All right, so now what I want to do now is try to explain why this gluing of these two trees actually yields a sphere. And the way that you check this is that you can use a theorem which is due to Moore from 1925. And what the theorem statement says is that if you have any equivalence relation on the sphere, which is topologically closed, and I'll remind you what this means in just a moment, and if you assume that each one of these equivalence classes is connected and not equal to the entire sphere, then the space that you get when you mod out by this equivalence relation is going to be a sphere if and only if none of the equivalence classes separate the sphere into two or more connected components. And what it means for an equivalence relation to be topologically closed is if you have two sequences, xn and yn, and you know that for each n, xn is equivalent to yn, and you also know that xn goes to x and yn goes to y, then the limits x and y are also equivalent. So it just means that it's continuous in some sense. And if you think about it, you know, this criterion here, this last part, it makes a lot of sense that this should be sort of the right thing, because you know, kind of what this is saying is that somehow you're not pinching off a bubble when you perform this identification. Okay, so now what I want to do is I want to explain how we can use Moore's theorem to show that what you get when you glue together two independent trees really does give you a sphere. Okay, so this picture here is exactly the same thing as what I showed you on the first slide. So we have our two independent Brownian excursions on the interval, and I've defined this equivalence relation on the sphere which is given by identifying points which are joined by a red line or a green line. And let me just emphasize, the way that you think of this as being an equivalence relation on the sphere is that this picture that I've drawn is on a rectangle, but then one of my equivalence relations glues together the boundary of this rectangle, and that's what gives you the sphere. Okay, so let me just tell you what the different types of equivalence classes you can get in this equivalence relation. So number one, as I just said, the outer boundary of the rectangle, that gives you an equivalence class. Another possible type of equivalence class is if you have a vertical line which does not share an endpoint with a horizontal line. So for example, you get something, something like this. You just have a single vertical line. And this corresponds to a point, or a time, where neither of the Brownian motions have a local minimum. Okay, the next possible type of equivalence class that you can have is a horizontal line which lies entirely below either at x or above c minus y together with the two vertical lines at its endpoints. So for example, this green line here, this is one equivalence class together with the two red lines, one at this side and the other at this side. Okay, so that's the next type of equivalence class. And the final type that you can have is if you have a horizontal line which lies either entirely below x or above c minus y, together with the two vertical lines which are at its ends, in addition to one additional vertical line which meets the excursion in the middle. So an example of this is this line right here. So if you look at this vertical line, this horizontal line, you have this green line together with the red lines at its left and right sides, and then this line here exactly touches the graph of c minus y here, and so in addition to the two lines on the left and right hand sides, you also get the middle vertical line here. And if you think about it, it's not very hard to see that these are actually the only possible equivalence classes that you can get in this type of picture. Okay. And it's also not difficult to check, and I'll leave this to you to think about on your own if you want to, that this equivalence relation actually is topologically closed and does not separate the sphere into two or more components. And therefore, by Moore's theorem, what you get when you glue the sphere together in this way is actually going to be homeomorphic to the two-dimensional sphere. Okay, so that's the construction of the sphere part of it. Where does the space-filling path come from? It comes from what you get when you follow these vertical lines from left to right. Okay? So you can imagine what you get when you just project this sequence of equivalence classes down to the quotient space. And this actually gives you a space-filling path because every point in the quotient space has to come from these two, a point on one of these two graphs. And every point on one of these graphs, of course, is touched by one of these vertical lines. And so if you follow them in order, you're going to visit every point in the space. And so this is the space-filling path. Okay, and again, we call this pair, which consists of a sphere and a space-filling path constructed in this way, the pianosphere construction. And the question that we really want to understand is what is the right way to take the pianosphere and embed it into the Euclidean sphere. And the reason for this is that, as I'll explain, this question is very closely related to the question of understanding how the scaling limits of random planar maps are related to Liouville quantum gravity. Okay, so all right, so since I think my talk is the first one on random planar maps in this conference, and it also seems to be the first one in kind of a series of different lectures people are giving on random planar maps today, I'm going to begin by just recalling for you the basic definitions for maps. So just to remind you, so a planar map is just a finite graph together with an embedding into the plane so that no two edges cross. And the faces of a map are just the connected components of the complements of its edges. And a map is a quadrangulation if each face has exactly 4 adjacent edges. And if you look at this picture that I've drawn here on the left-hand side, you'll see that this is actually a quadrangulation. And this is the type of map that we'll be interested in for the rest of this talk. And what we're going to look at are different types of random quadrangulations. So we're going to put different measures on maps with n faces, and I'm going to refer to such an object as a random planar map. And and so these random planar maps have a long history going back to Tutt in the 1960s, and since then there's been a huge amount of literature in different areas of math and also in physics studying different aspects of these maps. And here is actually one of my favorite pictures of what a random quadrangulation looks like. So this is a picture of a random quadrangulation. It has 25,000 faces, and it was embedded into the plane, or sorry, into three-dimensional space in some way. So one thing that I want to emphasize is that although the embedding that you see here is highly non-isometric, so it's not preserving the graph distance very well, this picture still serves to kind of show you or give you a feeling of what these objects are like. So, you know, the type of metric space that you get when you think of a random planar map is not, you know, kind of a nice smooth object. It's a very fractal and rough surface. And this picture, this was taken from the website of Jean-Francois Marquardt, who has a lot of really nice pictures of quadrangulations like this one. Okay. So there are a number of different types of laws that you can put on the space of quadrangulations with n faces. The most sort of natural one, or the first one that one is led to look at, is just the uniform measure. So if you pick a random quadrangulation with n faces uniformly at random. So that's one possibility. And another possibility, which is kind of a generalization of this, is you can take the uniform law on planar maps, and you can weight it by the partition function for the random cluster model when q is between 0 and 4. And so what I mean by this is that if you have a fixed quadrangulation M, the probability that you pick it is not uniform among all quadrangulations. It's proportional to the partition function for the FK model on the quadrangulation. So you weight it in this way. And when you have, when you pick a random planar map with this type of weighted law, it's natural not just to pick the map, but after you've picked the map, you can also sample a loop configuration from the random cluster measure. Okay? So in this case, you have not just a map, but you have a pair which consists of a map and then a collection of loops on the map. Okay, and then there's this general idea that whenever you have a structure like this, you can always encode both the loops and the map simultaneously using a dual tree pair. And let me just illustrate for you roughly how this works. So you imagine that you have a map like this, and then on your map you have a bunch of loops. So you have a nested family of loops, like that. And when you construct the tree structure, which is supposed to encode the map, what you do is you first pick a vertex, and you call that the root, or you pick a point on the map, and you call that the root. Okay. And then if you want to generate the branch in this tree, which starts at this root, and is targeted at another point in the map, what you do is you just sort of follow you sort of obey the loop structure in the map, and then whenever you get into a situation, let me just change my picture a little bit. So whenever you get into a situation where you're sort of forced to make a choice, where you can either branch in or you can branch out, you always go in the direction of the point whose branch you want to draw. So in this case, rather than going in, you go out, and you kind of go this way. And then maybe at some point, you're sort of led to follow these loops, you go around. Now here you're forced to make another choice, and then the choice that you make is that you branch towards the point that you want to get to. And if you do this, you'll eventually draw a path which goes from the root vertex to the target vertex. And I should emphasize that this construction that I'm describing here is exactly analogous to the construction that Antti described in his talk when he was talking about proving the convergence of the FK-Ising interfaces to CLE. Okay. And the idea behind a bijection, which is due to Scott, so he calls this the hamburger-cheeseburger bijection, is that he takes a loop-decorated map, like one of these FK-weighted random planar maps, and you can encode the map by describing the contour functions for the tree, which I've tried to indicate how it's constructed here, together with a dual tree. Now, I don't want to go over the exact construction of the hamburger-cheeseburger bijection now, but I think that later this afternoon in Shin Sun's talk, we'll see a much more precise description of how this bijection works. But anyway, what I want you to think of is that you can encode these random planar maps in terms of tree-dual tree pairs. And okay, so let me show you a picture to kind of give you an idea what this looks like. So this is a random quadrangulation. This is one that I actually sampled by implementing Scott's hamburger-cheeseburger bijection. And this is what one of the trees looks like in this map. Okay? And the other tree, the dual tree, looks like that. And so here you have this tree-dual tree pair, and then you can draw in the loop model. And in this particular case, this is for q equals 0. So this is just a uniform spanning tree decorated map, and this is the piano curve associated with the UST. But anyway, so the way again I want you to think of these maps is that you have your map, and then the way that you sort of build your map is you have your tree, your dual tree, and these are sort of glued together along a space filling path. And this somehow encodes the entire structure of the map. Let me say now a word about how this graph was embedded into the plane. So the way that I computed the embedding is that I started off with this quadrangulation, just abstractly, and then I subdivided each of the faces into the map into a bunch of triangles. And the way that I did it was so that each quadrilateral is subdivided into triangles which don't have any multiple edges. And the reason for that is that once you have a triangulation without multiple edges, you can always circle pack it. And so this is the circle packing associated with this quadrangulation. And if you're not familiar with circle packings, the way it works is that for each vertex in your graph, like this one here, you associate with it a circle, like that. And then the way that the adjacency relation in the graph is encoded is that two vertices, let's say this one and this one, are adjacent if and only if the corresponding circles touch. And this particular circle packing was computed using a very nice piece of software due to Ken Stephenson called CirclePack. And so if you Google this, you can find his website, and you can download the software. It's a nice Java program, and you can generate pictures which look just like this one. Okay. And this is just a picture of the same circle packing, except here I've colored the circles so that you can see the order in which the space-filling path visits the different vertices in the map. And the kind of questions that we really want to understand are, what is the limit of this particular embedding of a random planar map into the sphere? And the reason is that, of course, circle packings are connected to conformal maps. So this is one way of possibly approximating the uniformization of a random planar map. Okay, so that was just, oh, sorry, so something else I wanted to say. So yeah, so in the random planar map theory, there's a large number of convergence results which have been proved. Let me first just give you a very brief survey of just a small subset of the results which have been shown for uniformly random planar maps. So first of all, it was shown by Chesing and Schaefer that the diameter of a map with n faces is about n to the 1/4. And then Jean-François Legal showed that if you take a uniformly random map with n faces and you rescale distances by the factor n to the -1/4, then you can take a subsequential limit in the space of metric spaces. So you have some kind of metric space limiting object. And then finally, this subsequential limit was promoted to a true limit in these two independent works by Legal and Mirmont. And the limiting object is called the Brownian map. Okay, so this is just a subset of the results which have been shown for uniformly random planar maps. Now let's talk about random planar maps where you've weighted by the partition function of the FK model. So in this case, you can use Scott's hamburger cheeseburger bijection to encode your random planar map in terms of a pair of discrete trees which are glued together along a space filling path. So this is just the picture that I showed you earlier. And in this setting, it was shown by Scott in his paper on this that the pair of contour functions for your two trees properly rescaled converge to a pair of Brownian motions. And yeah, and so the the limiting law in Brownian motions depends on the value of q. And so, for example, when q is equal to 0, so you have a random planar map which is weighted by the partition function for the uniform spanning tree, you get independent trees in the limit. And for general values of q between 0 and 4, these trees are correlated, but they're correlated in kind of a simple way. And so what this says is that you can think of the scaling limit of random planar maps as corresponding to piano spheres. Okay, so this gives you the convergence of these types of maps with respect to certain special topology, and the limiting object is exactly this piano sphere construction that I described for you in the beginning. And this is the reason that trying to understand what the right embedding of a piano sphere is into the sphere is directly connected to understanding the scaling limit questions for random planar maps embedded into the Riemann sphere. Let me just mention one very interesting but seems to be very difficult question about the FK-weighted random planar maps, and that's that in the uniformly random case, it's well known now that the diameter of the map, when you have n faces, is n to the 1/4, but it's not known what the diameter is supposed to be for an FK-weighted random planar map. And it's believed that, it's, of course, some power of n, but it's not known what the value of alpha is supposed to be. And there's a lot of controversy. This is kind of a very controversial thing because there are different predictions that people have made. For example, there's this work by this physicist Wadowicki, which makes a very precise prediction. He writes down a formula for what it's supposed to be, but there's a lot of controversy as to whether or not this Wadowicki prediction is correct. And there's also been some simulation work that people have done. Some of it seems to confirm the Wadowicki prediction, but some of it also seems like it's inconsistent with this prediction. So this is a very interesting thing, but we just can't seem to pin down the right answer for this scaling exponent alpha here. And kind of the difficulty is that it's actually pretty hard, it seems, to do these simulations, because when you try to estimate this exponent, somehow you get so much variance that even with a very large sample, it just seems quite difficult to really get an accurate estimate of this alpha. Okay, so that was kind of the very brief survey on the scaling limit results for random planar maps. Now let me just briefly remind you of what Liouville quantum gravity is. So of course we already had a very nice introduction to Liouville quantum gravity in Remy's talk a couple of days ago. Now we were reminded again of what Liouville quantum gravity was in Johan's talk yesterday. And now let me do it one more time. So Liouville quantum gravity is the object that you get when you somehow take Lebesgue measure, or maybe the Euclidean metric, and you somehow weight it by the factor e to the gamma h, where h is a Gaussian free field. And this parameter we constrain to be between 0 and 2. And and so this object was introduced in the 80s by Polyakov and it's supposed to be some kind of way of generalizing the path integral to the setting of surfaces. And as Remy talked a lot about, it's not possible, to sort of make literal sense of this construction, because the Gaussian free field is not a function, it's rather a random variable which takes values in the space of distributions. And so it takes some work to construct this and make this mathematically precise. And this has been done in various works, and the way that you do it is that somehow you take your Gaussian free field here and you regularize it in some way so that you get a function, and then you try to show that your approximations converge as your approximations to this object converge as your approximations to the Gaussian free field get better and better. And so far, this has only been made sense of as a random area measure, and so the only kinds of operations that you can perform are that you can compute things like areas of regions, and you can also calculate lengths of curves. And over here on the right-hand side, this is another picture of what Liouville quantum gravity looks like. It's very similar to the one that Johan showed you yesterday. And what it is it's this square here, dyadically subdivided into smaller squares so that they all have approximately the same amount of area under the quantum measure. And what you see is that there are these regions, like these blue regions here, which are quite large in the Euclidean sense, but have roughly the same size in the quantum sense. And this is what it looks like with this value of gamma 0.5. And when you start to increase the value of gamma, so that the Gaussian free field is allowed to fluctuate more and more, this effect is just magnified. So finally at the critical parameter 2, you see these very, very large Euclidean squares, which are very, very small in the quantum sense. And as I'll explain on the next slide, Liouville quantum gravity is conjectured to describe, in a certain sense, the limit of conformally embedded FK-weighted random planar maps. And so here are some rough statements of the various scaling limit conjectures. So first of all, it's supposed to be true that if you take a random planar map picked uniformly at random, so not in the weighted case, then what you get when you conformally embed it into the sphere is supposed to converge to a certain form of Liouville quantum gravity, and the parameter here is supposed to be gamma equals the square root of 8/3. And there are various different ways of seeing why the square root of 8/3 is the right parameter, but I don't want to focus on that now. And more generally, it's supposed to be true that if you take an FK-weighted random planar map with a value of q, which is between 0 and 4, then the joint law of the random planar map and the loop configuration that you've drawn on top of it converges when you've embedded things into the sphere to Liouville quantum gravity decorated with a loop configuration, and this loop configuration is one of these CLE kappas. And so, in this construction, you have three parameters. You have q, gamma, and kappa, and the way that these parameters are all related is according to these formulas here. And by the way, the reason I've written kappa prime here is that I've gotten used to, whenever I have an SLE or a CLE, and the value of kappa is bigger than 4, I always write it as kappa prime. And so that's all that this means here. Okay, so these are the scaling limit conjectures. Now let me tell you about some of the results that we've proved so far. And before I jump into that, let me take a step back and just remind you of the general perspective that we're taking here. So the idea is that if you have a loop-decorated random planar map, we want to think of it in terms of a pair of discrete trees which have been glued together along a space-filling path. And what we really want to understand are what are the continuum analogs of these structures. Okay? So the continuum analog of the type of Liouville quantum gravity, of the random planar map is going to be a type of Liouville quantum gravity surface. This is what's called a gamma quantum cone. And the gluing of the continuum tree dual tree pair in the limit is going to be a form of SLE which is called space filling SLE. Okay. And we want to take the perspective that surfaces are close if it's true that the corresponding dual tree pairs are close in the sense that their contour functions are close. Okay, so this is a kind of special topology that we're looking at here. So this is different from, what you would get if you tried to conformally embed a random planar map and then show that, in some sense, the induced area measure is close to Liouville quantum gravity, or that the loops are close in the uniform topology. So here we're just looking at contour functions of the dual tree pair which encode the various objects. Okay, so that's the general perspective, and kind of the main result in this work is the following theorem. And what it says is that this surface, a gamma quantum cone, and I'll give you a more precise definition of it in just a moment, can be constructed in a unique way by gluing together a pair of Brownian trees, and the interface that you get when you glue them together is a space-filling SLE. Okay. So the way that you're supposed to think of this is that you have your surface. So let me just indicate the surface with this this box. And then on your surface you have a tree and a dual tree. So let me draw the tree in white. So there's some sort of a continuum tree. Sorry, it actually is a tree. So once paths merge, they don't separate. And then there's a dual tree. Let me try to draw this in blue. Maybe it looks something like that. And this is all sitting on top of one of these Liouville quantum gravity surfaces, this gamma quantum cone. And yeah, so you have this continuum dual tree pair. And once you've constructed these things, you can then try to build a piano curve. And what the piano curve does is it just snakes in between the dual tree pair. So it looks something like that. So you have some kind of curve. This is actually a space-filling path. It's visiting every point in the plane. And then what part of the theorem statement is that the length of the right boundary, right outer boundary of this this piano curve, together with the left outer boundary, so the blue side over here, that these boundary lengths actually evolve as a certain pair of correlated Brownian motions. Okay, so the lengths of the left and right hand sides of this space-filling path, which is somehow snaking between this tree and dual tree pair, evolve as Brownian motions. Okay, so what you're doing here is you start off with your Liouville quantum gravity surface. So you have your surface, and then what you do is you decorate it with this this path, this space-filling SLE. And then by looking at how the left and right boundary lengths of this path evolve in the quantum sense, you produce a pair of Brownian motions. Let me write LT and RT. Okay, so these again indicate the evolution of the boundary lengths of the left and right sides of the path as you go. Okay, and so one part of the theorem is that if you start off with a Liouville quantum gravity surface and space-filling SLE, you get your L and R. So these things exactly appear. And then the second part of the theorem statement is that if you see L and R, the two Brownian motions, then there's actually a unique way to embed them back into Liouville quantum gravity like this. Okay? So again, the Liouville quantum gravity plus space-filling SLE determines your pair of Brownian motions. And conversely, if you just see the Brownian motions, then there's a unique way of constructing the surface and the path. Okay? And the way that you're supposed to think of these Brownian motions again is that these are describing Brownian trees. Okay, so that's kind of the main result. Now let me make a few comments about it. So first of all, if you combine this result with the result due to Scott on the hamburger-cheeseburger bijection, this tells you that random planar maps weighted by an FK model converge to CLE decorated Liouville quantum gravity, but it's with respect to this sort of special topology. So here we say that two loop decorated surfaces are close if it's true that the corresponding contour functions of the dual tree pair are close. Okay, so you get convergence just with this special topology. And let me also remind you that for planar lattices, so far it's been shown that the FK models, the loops associated with the FK models, converge to CLE in certain special cases. So for example, for Q equals 0, we know that the uniform spanning tree converges to SLE8. This is this very famous work of Lawler, Schramm, and Werner. When Q is equal to 1, which corresponds to percolation, we know that the interfaces converge to CLE6 from the work of Smirnov and also Kamiya and Newman. And then finally, in the FK easing model, we know by the work that Antti told us about yesterday that the interfaces also converge to CLE 16 over 3. But this result here is telling you that in the random planar map setting, with respect to this very special topology, you actually get convergence of all of the FK models for every value of Q between 0 and 4 to CLE with the conjectured values of conjectured relationship between Q, gamma, and kappa. Okay. And let me just emphasize again, one of the main parts of this theorem is that you can recover everything by just seeing the contour functions of the continuum tree dual tree pair. So just like in the random planar map setting, if you see the two trees, you can build the map, and it's also true in the continuum that if you see your two continuum Brownian trees, then there's exactly one way to construct Liouville quantum gravity decorated with the space-filling SLE. Okay, so this is the kind of main result. Let me just illustrate it pictorially one more time. So here we have our random quadrangulation, and it's represented as a gluing of the red tree and the blue tree along this green path. And in the continuum, what you get is a Liouville quantum gravity surface decorated with a continuous space-filling path. And here's what it looks like. So this is actually the SLE6 version of it. And again, somehow the theorem statement is that the processes which describe the boundary lengths of the space-filling curve as you go encode the structure of the scaling limit of one of these random planar maps. Okay, so that's the kind of main theorem. In order to prove this result, what you have to do is you have to develop a sort of calculus of random surfaces. And so what we have are these quantum wedges, and I'll explain the definition in just a moment. We also have something called a quantum cone, and then finally some different laws on finite volume surfaces. So there are quantum disks and also spheres. And what can you do with these surfaces? Well, you can weld them together and you can cut them into pieces. Just like if you have a graph, you can glue graphs together and you can cut them into pieces. And it turns out that when you perform the welding operation, the interfaces between the surfaces are SLE variants. And conversely, when you cut these surfaces, the right type of interface to cut along is an SLE path. And there are kind of two big external inputs that go into making the whole thing work. The first is what we call the imaginary geometry. And what this refers to is a calculus of flow lines of e to the I h, where h is a Gaussian free field. So there's some precise way of making sense of this type of vector field, and the paths that you get when you flow along this type of vector field turn out to be SLE paths. And the other big input is a conformal the very important conformal welding result, which was proved by Scott. And what it says is that basically what it says is that if you have two of these quantum wedges, so the way that you should think of this is sort of a generalization of a Euclidean wedge, then you can take them and you can glue them together along their boundary length, just like you could glue together two graphs according to edge length. And when you take this picture and you glue these things together and you embed it into the plane, then what you get is a new quantum wedge decorated with a space filling, just a regular SLE, which represents the interface between these two paths. And this is just sort of a generalization of the fact that, in the Euclidean setting, if you take two Euclidean wedges like this, then there's also, a natural gluing operation, which is that you just identify these things according to boundary length. And when you do that, you just get a bigger wedge together with a path that represents their interface. And in the Euclidean setting, which corresponds to gamma equals 0, the interface is just going to be a straight line, which is SLE 0. And what happens in the quantum setting is that the interface is just SLE kappa for a positive value of kappa. Okay. And in this work, he shows that in a certain sense, this is the kind of canonical way to glue together surfaces of these types. Okay, so what I want to do now is just tell you a little bit about the different types of random surfaces which appear. So the most basic object is this quantum wedge. And the starting point for a quantum wedge is that you imagine that you're working on a Euclidean wedge with a given opening angle. And you have on your Euclidean wedge an instance of the free boundary Gaussian free field. So you have your Gaussian free field on your wedge. And then what you do is you perform a change of coordinates, which takes you from your wedge to the upper half plane. And when you perform the sort of right change of coordinates that preserves the quantum measure associated with this free boundary Gaussian free field up here, the object that you get downstairs is going to be a free boundary Gaussian free field plus, this constant q. So q is equal to 2 over gamma plus gamma over 2 times the log of the derivative of this, this conformal map. But this map that takes you from the upper half plane to this wedge is just given by a power of z. And so what you get from this, this term here is just going to be some constant times the log function. Okay? So what you get when you start off with the free boundary Gaussian free field on the wedge and you map to the upper half plane is a free boundary Gaussian free field down here plus some multiple of a log. But the free boundary Gaussian free field is only defined up to an additive constant, and that's kind of a problem because if your field is only defined up to additive constant, that means that the measures that you define from it are only going to be defined up to multiplicative constant. And so what you need to do is you need to fix the additive constant in a canonical way. And once you do that, the result is one of these quantum wedges. So it's basically just free boundary Gaussian free field plus log, but you fix the additive constant in a certain way. And the space of wedges, it's natural to parameterize them in different ways. So one way is just in terms of the multiple of the log singularity, that's alpha. And then another way, which is very natural, and I'll explain why in just a moment, is by this parameter here, which we call the weight of a quantum wedge. So it's just some number which is derived from the multiple of the log singularity. And then a quantum cone is very similar to a wedge, except the difference is that the starting point is not a free boundary Gaussian free field on a Euclidean wedge, but rather it's a Gaussian free field on a cone with a given opening angle. And if you start off with this setting, you can also just map to the whole plane using a power map, and what you get is a whole plane Gaussian free field plus a log singularity. So cones and wedges are very, very similar. And you can parameterize the space of cones in different ways. So one way is you just keep track of the multiple of the log singularity that you get. And then the other way is that there's also a very natural weight parameter that you can associate with a cone. And I'll explain why this is natural in just a moment. And then finally, you also need to understand a bunch of different laws on finite volume surfaces. So these are quantum disks and spheres. And the kind of starting point for the construction of these objects are the free boundary Gaussian free field and certain Bessel excursion measures. But I won't describe these constructions in detail now. Okay. And so what are the basic operations that you can perform? So first of all, there's a generalization of Scott's conformal welding procedure to general wedges. And again, the way that it works is that you can start off with two wedges, like these guys here, and you can glue them together just by identifying the right side of this guy with the left side of that guy according to according to quantum boundary length. And what you get after you perform this gluing and you embed it into the upper half plane is a wedge, which is parameterized by the upper half plane, together with this SLE path, which represents the interface between the two original wedges. Okay, and so in many ways, this is just analogous to the operation of gluing together regular Euclidean wedges, but it can be a little bit different because unlike regular Euclidean wedges, these quantum wedges don't have to be homeomorphic to the upper half plane. So in this picture over here, I have a fat wedge, so this one's homeomorphic to the upper half plane, but the guy on the right-hand side is a skinny wedge. So rather than just being one kind of connected component, this is a whole sausage chain of surfaces. But still, you can glue together the fat wedge and the thin wedge, and again, what you're going to get is a bigger wedge decorated with a path which represents the interface between the two wedges. And there are more possibilities too. So you can have two skinny wedges glued together, and if they're not too skinny, then what you get when you glue them together is going to be a fat wedge. But if they're both very, very skinny wedges, then what you get when you glue them together is just going to be another skinny wedge. Okay, so there's this sort of theory of welding that one can develop. And the reason that this weight parameter is important is that it turns out that this is what is additive under the welding operation. So whenever you weld together wedges of weight W1 and W2, the resulting wedge is just going to be a wedge of weight W1 plus W2. And one of the kind of very important facts in all of this, it's always sort of an interesting thing in the Gaussian free field stuff, it's sort of what determines what, and that's that if you see these two wedges, the left one and the right one, then there is a sort of unique way of recovering what this interface had to be. Okay, that's the welding operation, and then the cutting operation is just the reverse of this. And the way it works is you start off with a wedge, say on the upper half plane, and the way you slice it is you just draw an independent SLE on top of it, like this. And then what you're going to get on the left-hand side of this path and the right-hand side are going to be independent quantum wedges. So this is one operation that you can perform. Another operation that you can perform is that you can weld together many wedges. So you might not just have two, but you could have a whole series of wedges like this. And if you glue all of these wedges together, in this case I have 4 of them, then what you're going to get is a big wedge whose weight is going to be the sum of the weights of the little wedges, and the interfaces between the different wedges are all SLE type processes, and they can be described simultaneously as flow lines of the Gaussian free field. Okay, so these are the welding operations for wedges. There's also welding operations that you can perform for cones. So here what I'm doing is I'm starting off with this is a fat wedge, and then what I'm doing is I'm taking this wedge and I'm just identifying its left side with its right side. Okay, so you can just glue the wedge to itself according to quantum boundary length. And just like if you take a regular Euclidean Euclidean wedge, if you glue its left side and right side, you're going to get a Euclidean cone. In the quantum setting, when you glue the left side and the right side of a quantum wedge, you get a quantum cone. And the interface, which describes where the boundary between left side and right side was, is going to be an SLE process, a type of whole plane SLE. And this operation works both in the setting where the wedge is fat, like I have illustrated over here, but also for skinny wedges. The difference is that when you glue a skinny wedge to itself, you get a quantum cone where the SLE process is going to be self-intersecting. And again, this is just reflecting the fact that the left and right sides of this quantum wedge actually intersect. And just like in the quantum wedge case, there's an inverse operation where you start off with your cone, let's say over here, and then you get your wedge just by slicing the cone with an SLE. Okay. And Yeah, and actually once one has this theory, this sort of generalized theory of cutting and welding for quantum wedges, that's basically enough to prove the Brownian motion statement for an exploration of a quantum cone by a space filling SLE. So these are really, really crucial in the whole thing. So here, kind of what I've described in the previous two slides are what happens when you put a simple SLE on top of a quantum wedge or cone. It's also natural to put self-intersecting SLEs on top of quantum wedges and cones. And so here, I have a certain type of wedge, and I've drawn on top of it an SLE process, and I want kappa to be between 4 and 8 because I want it not only to be intersecting itself, but also to be cutting off regions. And it turns out that the sort of regions that this process is cutting off, so these little bubbles here, if you view these as little surfaces, these actually have a Poissonian structure, so you can describe their exact law in a certain very precise sense. And it turns out that these little surfaces are actually independent of each other when you condition on their quantum boundary lengths. And moreover, if you evolve your process, your SLE process in time, then the way that the left boundary of the SLE and the right boundary evolve are given by independent kappa prime over 4 stable processes. Okay? So just what this means is that if you keep growing a little bit more of this process, then kind of the change in the length of the left side and the right side are just given by this type of Liouville process. And the jumps of the two Liouville processes, what these are encoding are the boundary lengths of the different components that you cut off. So sort of as you go, whenever you cut something off, your boundary length is going to make a negative jump, and that just corresponds to the length of what you're separating. Okay. And what this is kind of very interesting because this tells you that there's a way of viewing an SLE process when kappa is between 4 and 8 as a gluing of stable Liouville trees. Okay? And the way that this works is that you have your two processes, x and y, from the previous slide. So remember, this is the boundary length of the left side of the curve. This is the boundary length of the right side of the curve. And these processes only have negative jumps because you can only jump when you cut a region off. And you can construct an SLE out of this picture by, what you do is you first think of taking each one of these jumps. This is what's supposed to correspond to a disk cut off by the SLE. And you just sort of fatten it a little bit. So you get a little region like that. And then you can take this picture and you can glue it together. And the way that you glue it together is you just identify points which can be reached by a common horizontal or vertical line. Okay? And the reason that I fattened up the jumps this way is that when you perform the gluing along the vertical line which says here, this sort of exactly pinches off this little lens-shaped region into a disk. And when you glue everything together, what you get are a gluing of these two Liouville trees. And what the previous result is telling you is that this is a way of representing what SLE is when kappa is between 4 and 8. And it turns out that this actually gives you a unique representation. So if you see the processes which describe the evolution of the left boundary length and the right boundary length of your SLE, together with the little disks that you cut off, then there's exactly one way to recover the SLE. And what this means is that you can take questions, you can formulate questions about SLE processes when kappa is between 4 and 8, and you can convert them into questions about stable processes, kappa prime over 4 stable processes. And I want to give you an example of one question that I really like that seems to fit very well into this framework. And so here's the question. So what you do is you imagine that you have your SLE. So let me draw you another picture of an SLE. So here's the upper half plane, and you draw your SLE. And then as your SLE goes along, it cuts off these components. So you have all these regions that it cuts off. And what you can do is you can put a graph structure on these components. And the way that you do it is you say that two components, U and V, they're adjacent if their boundaries have non-empty intersections. Okay, so this defines a graph structure. And then you could ask the question whether or not the graph of SLE components is connected or not. And what this means is, whether or not it's true that starting from any component here, you can get to another component by just a finite chain of adjacent components. And yeah, one of the reasons that I really like this question is that there's another question which is very similar to this. I think this question is due to Yuval Perez and Wendelin Werner. And the question is, do the same thing, not when you have an SLE, but rather you have a Brownian motion. So you draw a Brownian path and you can try to form the same graph, then you can ask whether or not it's connected. And one of the reasons I like the SLE question is that this seems like it's very interesting, but maybe the Brownian motion question is very interesting, but maybe the SLE one is easier, because one of the key differences between SLE and Brownian motion is that SLE does not re-enter the components that it cuts off. But at the same time, when you think of the SLE question, in terms of sort of the geometry of this picture, it seems like it's pretty hard also. Also, it seems like it's not straightforward to answer this. However, once you make this change of perspective, you can kind of erase all of the two-dimensional geometry, and it just becomes a question about two independent stable Lebesgue trees. And it's whether or not, when you perform this gluing operation here, it's possible to get from one jump to any other jump using only a finite number of equivalence classes. Okay, so now in the last few minutes, what I want to do is I want to just take a step back and give you a little bit of discrete intuition as to why you would expect any of the results that I explained today to be true. Like, why does it even make sense? And the reason I want to explain this is that these seem like they're kind of weird things. If you take a quantum surface, you cut it with an independent SLE, why should you get independent quantum surfaces? And the reason is that these are just the natural sort of continuum analogs of different operations that you can perform on random planar maps. So here's one example. So here I have a domain Markov random planar map. I've colored the boundary vertices on one side to be red, and the other side to be blue on either side of this marked edge. And then, what you can do is you can imagine performing a percolation exploration starting from this marked edge. So maybe the first triangle that you see here is this red one. And then because this map is domain Markov, what that means is that the conditional law of what you haven't seen is exactly the same as the law of what you started with. Okay? And so if you keep exploring like that, then because of the domain Markov property, the boundary lengths of the left and right sides of your cluster are going to have independent increments. And it's also going to be true that the law of the components that you cut off have an IID structure. And the continuum statements are just the natural continuum analog of this, this discrete picture here. Okay. All right, so now let me just finish with a couple of final thoughts. So first of all, one of the things which I find very interesting is that over the last 15 years now, since SLE has been invented, there are sort of many different perspectives of what what SLE is. So when Schramm invented SLE back in '99, the way that he defined it is he said it's the object that you get when you take the Leibniz equation, you take the Cordell-Leibniz equation or the radial version, and you solve it where what you feed into it is given by a Brownian motion. That's what SLE is. And since then, there have been many other ways which have been developed for how you can view SLEs. So another perspective is that you can view SLE as the flow lines of the Gaussian free field. So you also have Gaussian free field flow lines and level lines. And this started with the work of Schramm and Sheffield on the level lines for the Gaussian free field. This is another useful perspective for studying SLE. You can also construct SLEs by looking at outer boundaries of loop soup clusters. This is another very useful perspective. You can also construct SLEs by gluing together the interfaces when you perform gluings of quantum surfaces. And what I started to describe to you today is another perspective where you can view SLEs as what you get when you glue together different types of trees, so Levy trees and Brownian trees. And each one of these perspectives, turns out to be really, really powerful, and it's easy to prove things, using some representations, whereas, certain questions, they're much easier solved when you make one of these changes of perspectives. Okay, now the types of convergence results that I described today are with respect to this one particular topology, where you say that surfaces are close if the contour functions of their dual tree pairs are close. And this is, in some sense, it's kind of a weak topology. And of course, one wants to promote this to stronger types of convergence. And the sort of ultimate result, of course, would be to show that what you get when you conformally embed one of the random planar maps into the sphere actually converges to Liouville quantum gravity. But there are also intermediate topologies that you can consider. And I think we're going to hear more about this type of question in Shin's talk this afternoon. One other thing that I didn't talk about today, but it's also embedded in this work, is that we provide a way of making precise the types of arguments that a physicist like Bertrand would make for different exponents using the KPZ relation. So basically what he does is he sort of interprets a random fractal, as sort of locally looking like a gluing of quantum wedges of the type that I've described here. And there's kind of a mechanism of extracting from that what the right dimension of the fractal is supposed to be. And there's a more mathematically precise version of this, which is described in this work. And then finally, I didn't say anything today about something else that we've been working a lot on, which is QLE, which is another way to relate scaling limits of random planar maps to Liouville quantum gravity. But I just want to say that both this work here on the mating of trees, this is very closely connected and sort of forms the basis of QLE. And with that, I'll stop.
We're running a bit tight, but there's maybe one or two quick questions.
Yeah, can you say a little more in which sense you get SLE from the gluing of your stable trees? Because it's not embedded in the plane, of course.
Right. So the statement is that, okay, let me draw a picture. So the statement is that what happens when you have a type of Liouville quantum gravity surface, and you explore it by one of these self-intersecting SLEs, then what happens is that the evolution of the left boundary length and the right boundary length evolve as a stable Levy process. So from this picture, you generate a pair XY, and these correspond to the two Levy processes. But there's more information in this picture. You also get the sequence of disks that you cut out, like this. So you have, let me call that D. So you produce from your Liouville quantum gravity surface decorated with an SLE, a triple, which consists of the left boundary length, right boundary length, together with these surfaces. And the theorem statement, or one of them, is that if you see this triple here, then you have enough information to recover the original picture. So this is a measurable function of that, but this over here is also a measurable function of this. And, okay, okay, and then if you just want to ask a question about the topology of SLE, so you don't want to ask something about its specific embedding, then you could just erase this information here. You can forget about the actual quantum disks, and you just have your two Levy processes. And these determine the entire topology of the SLE. And then the way that it works is that is just in terms of this gluing. The topological structure is described entirely in terms of that.
thank Jason again.